Okay. So good morning, everyone. My name is Busola Oronti, and I'm a doctoral researcher at the University of Warwick in the UK. So today, I'm going to be talking about the electrical safety of medical devices and equipment. And I'm going to try to make it as interactive as possible. So the first thing I would want us to do, can you see my screen?
Yes, we can see your screen.
Yeah. So I hope nothing is blocking it. That's why. So let me, sorry, just right. Okay, now I want you to notice there are a few things here. I have a website that I would want you to go to in the during this presentation, and you can access that website. You can access that website by joining the web at this address. When you go to that address, you type in this code, and then you'll be able to respond to whatever activity I'm putting up. If you don't do that, you can scan the QR code, and then you get the link, or you type in this link. So I want us to do that now, just to get prepared. And then you can also join by text by using this is the text. You send this text to this number, and then you'll be able to access the activities that we have. Okay, so let me move on. Let's start. What? Okay. So I'm going to start with an activity that I just want, it's like an icebreaker, and I want to have an understanding of what we understand about this topic now. So let me just go to the activity. I hope we're all there. I will activate the activity soon. So this is our first activity, and let me activate it. So what I want is that I want you to tell me how often you do come in contact with electricity in your daily job, or maybe in life. I want to see, I want to have an understanding of how that is for you. Are we there? Please let's access the activity and put in whatever we have. We will see what is going on here if we look at it. So, are you there?
No.
I can't see anyone there.
Hello?
Do I?
Yes, we are with you. We're with you.
Can you access the site?
Yes, we can, but you need to zoom like. Username and password.
I think I've activated it now. Are you? Ah. Okay, I didn't have it never. That's very good. And I have 67% saying always. So that's a good start. So yeah, let's go to the next activity. Yeah. So let me activate it. So when you're thinking about electricity, what comes to your mind? What word comes to your mind? I want you to put in any word that comes to your mind. Just type it in and let's see. This is a word cloud. So the word that comes in most frequently will take the preeminence. Okay, we have caution, physics, everyday shock, electron, okay. Electric, okay. Shock, electric, electron, NEPA, I like that. Okay, all right, that's good, that's good. Okay, yeah, I'm getting somewhere with this. So, okay, let's stop this activity for now and then let's continue with the slide. Okay, so now let's start with the presentation. Why are we looking at this topic? We're looking at this, why is electrical safety significant? In the first instance, medical equipment can expose patients and caregivers to potential hazards, such as electrical shocks. And then there's always the danger of leakage current resulting from improper grounding and electrical isolation of the device. And also, because of the way our body is constituted, 70% of our body is made up of fluids. So that is also a potential danger. And apart from that, on the surface of the body, you can have body fluids, you can have various conductive solutions and gels and such whatnots that can create a vulnerable environment for the human body. If we zoom here, just try to look at, zoom in on this picture here, we'll see that one of the most common ways in which an electric shock can happen is when there is a broken ground wire. And I mean by ground wire, I mean the wire that takes any excess current on the device or the equipment you're working on to the ground. For example, here we have a broken wire. And the thing about current is that it follows the path of least resistance. So when there is a broken path here, the current will try to find another way to go to the ground, and that will be through somebody's body, and that will not be me or you. So that is what happens, and then that's when we now have a shock. Okay, let's go to the next slide. Now we'll have some, I know we all know these things, but let's just go through them. Electric current, which is a stream of charged particles moving through an electrical conductor or space. The voltage is the difference in electric potential between 2 points. Now, when we're talking about electrocution, this occurs when current passes through the human body. And the measure of electric shock you can experience is directly proportional to the amount of current passing through the body and not the voltage. Some people think it's the voltage, but it is not. And then it works by the principle of Ohm's law. So the higher the resistance that there is, the better one is able to withstand electric shocks. Now, electroporation, this is damage to the cell membrane due to the application of a large voltage to living tissue. Now, I will look at the effects of electric current on the human body. Some of the effects include involuntary muscle contraction, and we call this tetany. And this is usually caused by the DC and AC components, sorry, the amplitude of the AC component of the AC waveform or DC. Then you can also have burns resulting from the heating effect, because we know that when there is a resistance to current, heat is generated. And when this is generated internally, then heat is generated internally in the body, it causes burns. And this can result in internal organ damage. You can see this can be caused by the AC and DC components of current. Then we can have cardiac arrhythmias. That is when your heart starts beating like abnormally. So when AC current passes through the heart, it can cause the heart to start beating abnormally. And then you can also have damage to nerve tissue. And this can destroy the brain and spinal cord and cause some very, very definitive issues in the body. then we can have ventricular fibrillation, because a current will always try to find the path of least resistance. So we have blood flowing in our ventricles, in the capillaries, in the blood system. So this is a very easy path for current to flow through. And then that's why most likely the current will go through the heart, thereby causing cardiac or respiratory arrest, which is mostly caused by DC. And then the final thing is death, which can be caused by AC and DC. Now, some of the factors affecting the way the body interacts with current is dependent on, first and foremost, our skin resistance. Now, in a normal situation, you will have between 10 kiloohms to 1 megaohms of resistance on the surface of your body. Assuming you don't have cuts, you don't have like gels, your skin is not wet. So you have that kind of resistance on the surface of your body. Now, internally within the body, the resistance is between 200 to 300 ohms. Now, when we're talking about voltage, when it becomes important is the voltage at which the skin breaks down, and it's very high. It's very high voltage. That's like, as you can see, 500 volts. And so what this means is that you can actually have extensive damage inside the body that doesn't show on the surface, because if it takes 500 volts for the skin to break down, a lot of things could have gone on inside the body at that point in time. So also another factor to consider is the length of time of contact, the magnitude and intensity of the electrical current, then the minimal let-go current. Now, what I mean by the minimal let-go current is when there is somebody has an electric shock. Now, for example, if you grab a biro. Hello?
Yeah, please go on. You'll be muted now.
Okay. Can you see me?
Yes, we can.
Okay. Now, if you grab a biro, like you, for example, experienced people who deal with electricity, they do not handle, like, they want to touch a cable or they want to touch like a panel. They will not use their hands to grab it like this, the way I'm holding this pen. What they would do is to use the back of their hands, because when an AC current flows through the body, we have our hands, we have extensors, and we have flexors. Our flexors are the ones that close, our extensors open our hands. Normally, the flexors are stronger. They have a stronger effect than the extensors. So when a current passes through a body, especially when it is at a low voltage, between 50 to 60 hertz, the hand grabs on. The muscles are not able to let go of whatever is being held. So when you want to touch something, you're not, a medical device, a cable you're not sure about, it's better to use the back of your hand, because if there is anything that happens, the hand will clench in the opposite direction. Now, another thing that we need to know is that AC and DC current, they have different effects on the body. Okay. Now, let's look at the general effects of electric currents. Below 1 milliamperes, you cannot feel anything. So a lot of us get shocks below 1 milliampere every day, and we don't feel anything. At 1 milliamperes, then you tingle, your fingers will tingle, or maybe some part of your body will tingle. When it gets to like 5 milliamperes, then you can experience slight shock, not painful, but it's something that you feel, and then the involuntary reaction it will set in, where, like I said before, the let go effect, and then which can lead to indirect injuries. Now, electrical shock affect women and men differently. For women, women have a lower range, that's between 6 to 25 milliamperes, while men have a higher range, that's between 9 to 30 milliamperes, before they can experience the effects of an electric shock. So and then you have painful pain, loss of muscle control. And then the freezing current, which I earlier said is the can't let go effect. Now, between 50 to 150 milliamperes, there is extreme pain. You can have respiratory arrest, muscle reactions, and then possible death. When it's going to 1 to 4.3 milliamps, then the heart can go into fibrillation. There's muscular contraction and nerve damage, which can likely lead to death. And then 10 milliamperes, certainly cardiac arrest, severe burns, and death is very probable. So generally, currents above 100 milliamps are almost always fatal unless immediate medical attention is provided. So I have said a lot of things here. So I'm going to test our knowledge in a minute. I want you to go back to my page, and then I'm going to activate some questions and then see how you do with that. So let's go to the next question. So the question, it will show in a minute. I want you to identify all possible causes of electric shock. Okay, everybody saying contact with faulty overloaded. Okay, yes, I can see. Okay, we're still having people voting. We'll see how it goes. Okay. Okay, well, I just wanted to stabilize a bit and then we'll see our final answer. Okay. So some of us have said 13% contact with faulty overloaded electrical outlets or switch. Faulty appliances, I think I showed you the answer before. Then water liquid on skin surface when working with electrical outlets or appliances. All of the above, everybody, someone is saying all of the above here. Really, you can get electric shock from lightning from thunderstorms. And in fact, sometimes when you have your devices plugged into the wall, sometimes lightning can, there's a way that lightning can affect your electrical device and cause a fault, which may be unknown to you. And it can actually cause, an electric shock. So this is the final answer. Let me just, the correctness. This is it. I did not take this because it's not just about faulty appliances. If you don't touch that faulty appliance, you're not going to get an electric shock. So it's just testing our reasoning. Okay, so now let's go to the next question. The next question, this will involve some thinking. Let me activate it. So I want you to tell me why birds sit on electrical post wires and do not get electrocuted. If you know the reason why. Okay, I have an answer because there is no closed circuit at this case. Insulating foods, fine. Okay, does anyone have anything else to say? Okay. The best claw is insulated. Okay, fine. Because the wire is not in contact with the ground. Their feet are insulated. Okay, these are very interesting answers, and they are right. The skin is like plastic material, fine. Their scale foot is an insulator. Okay, so I think most people are saying because the foot is insulated. There's no blood flow in their talons. Okay, that's nice. Okay, all of you are right. Okay. Okay. Okay, so I can see that what most people are saying is about the foot, which is right. The foot is insulated, but you know that sometimes it depends on the, yes, because current flows through the list. All right, these are very, but we have to stop now. So, but one thing I want to say about this is that the birds are able to do this. You know, remember when we're defining voltage, we said it is the electrical, the potential difference between, oh God, they are playing with their lives. We said the potential voltage is the potential, electric potential difference between 2 points. You can see that these birds, they are basically on the line. It is the same line. It is the same, for each of those birds, they have placed their foot at different points on that line, and there is no potential difference. Fine, yes, their feet is insulated, but you know insulation can break down. So basically, the major reason why they are not getting electrocuted is because they're on that same line, and there is no difference in potential on that line. So the current passes through them and goes on, and it doesn't do them any harm. But if they were to touch something else, like a metal or something else that has a different potential, then they will really be playing with their lives. Okay, let's go back to the... Now, let's look at some codes and standards. So for electrical safety of medical equipment, we have established codes and standards. And now a code is, both of them are documents, but the difference is that a code is generally adopted into law by authority that has jurisdiction. So you can be prosecuted. On the other hand, a standard is a mandatory requirement. Both of them are mandatory, but for a standard, compliance tends to be voluntary. So if I have a list of standards I'm telling you to follow for the safety of your equipment, you can decide that out of 10, you're going to do 3. Nobody's going to call you to a court of law, but there are consequences like we're talking about here. So we have codes and standards for the regulation of medical devices. And the one that is particularly relevant to the safety of when we're talking about medical device is the IEC 60601. It forms the basis of for most national medical equipment safety standards in many countries. For example, in the United States, the FDA requires that all medical devices be safe and effective. They use this. They use IEC. And then for Europe, they start with EN. You can see EN is still the same number. It's because it's in Europe that's starting with EN. So whether you see IEC 6601 or you see EN 6601, they're talking about the safety of how to maintain the safety of your medical devices. In Africa, we don't have any regulation, and we follow what the other people are doing. But really, there are really issues in Africa that we have to look at. That might need us to tweak regulations that are suitable for the kind of environment that we are in. And this is something that I see it as a line of research that we must take on just to make sure that we have some things that are suitable to our environment. Now, in high-income countries, these are the things you would expect. Yeah, you have manufacturers of medical equipment. Most of them are from high-income countries. They ensure that all safety regulations during the design and manufacture of the medical device are complied with, and that the equipment is safe. Now, hospitals ensure that equipment remains safe during usage. They have very strict standards and they follow it. Then electrical safety tests are compulsory after every repair of a medical equipment. Then safety tests are part of the preventive maintenance procedure. And finally, they have well-defined safety standards and test procedures, which we've seen. But in low-income countries, what do we have? Electrical safety standards are hardly applied. Monetary organizations do not exist or are not doing their jobs. In fact, I think they exist, but they are not doing their jobs. Hospital management is not aware of the importance of safety tests, or maybe they lose the significance of it. And then we have technical departments who may not have time, money, or expertise to implement safety tests. And then we have specialized measurement equipment for which may not be available to make certain tests. So some of the common challenges, as said, in a regular environment, you'll probably find faulty electrical installation in hospitals. You have missing fuses and residual current devices. I mean, circuit breakers generally. You have broken wall sockets, sometimes missing power plugs, leakage current in sockets. I worked in a lab when I was in Nigeria. It was a lab, it was an electrical lab. And the sockets, you're not supposed to read your live and neutral are not supposed to read when you put your meter in. You're not supposed to have any leakage current, but all the sockets were reading one to another, which is a problem. And we've seen this in other countries, in other African countries too. So, when we are talking about the safety of medical devices, we need to follow test procedures. The first thing to do is to check the environment of the equipment, especially for low-income countries. Don't go to the equipment first. You want to test an equipment first. Yeah, check the environment. Check what's wrong with it, like we said before. Check whether you have broken sockets and stuff like that. Maybe some fuses are not where they should be. Those are the things you should check first. Then secondly, you can now go to do visual inspection of your equipment. And then finally you conduct the test. If you have a test equipment, fine, it makes life easier. But if not, you can use a common digital multimeter. So then you must have a knowledge of what you want to test. What tests should be carried out, how the test should be done, and how high the limit values should be. These are things that you need to know, and you don't need to have them in your head. There's a documentation. For example, I put here a QR code that you can use to download the IEC 6601. This will take you there if you focus on that QR code. It's an updated version of the document, so they have a lot of cancellations and all that, but it will give you what you need. It's very detailed if you're interested in something like that. So make sure you refer to all necessary documentation and manuals. So when we're talking about visual inspection, we're talking about looking at the outside of the medical equipment and then looking at the inside, if that is allowed, if that's permitted. So when we're talking about the outside inspection, look at the wall sockets. Are they in good working condition? Is the power plug okay? And of the correct system, because you can have the American system and then the British system. We use the British system in Nigeria. Are the contacts clean, or are they charred? So these are things to look at. Is the power cable damaged? Patched or brittle cables should be replaced immediately. Then pull the cables at the on the equipment side and on the plug side. Check the strain relief of the cable. Is it tight? So these are the things you can check outside of the equipment. In the equipment, inside the equipment, you can look for signs of overheating and burns. And then you check whether all the cable connections are tight. Look for loose cables. Are there bare wires? Are the fuses correct? Sometimes, and I've seen that done a lot in Nigeria, fuses are bypassed. You use a piece of wire to become a fuse, which will not break. That wire will remain in place if there is there's a flow of current that is beyond the admissible limit, and it's a hazard to the person handling that equipment. So, talking about medical devices, we have 3 classes. We have classes 1 to 3, and you can see the symbols, like they have nameplates. Medical equipments generally, they have nameplates, or if you look under them or somewhere, they will have some details about them. So, and then you can see, if you see this symbol, you know that's a class 1 equipment, or sometimes there will be no symbol. If there is no symbol, it's a class 1 equipment. If this shows a class 2 equipment, and this is a class 3 equipment. So the basic things to know about a class 1 equipment is that apart from the insulation, we also have what we call the protective earth connection, the PE. So for this, that's when you have a 3-pin plug. If you have a 3-pin plug, then you will have a earth connection. So, and then if the insulation breaks down for any reason, then the parts of the equipment cannot become live for any reason, because whatever extra current you have will go through the earth. For the class 2 device, you don't have a connection to the earth. What you have in this case is a double insulation between any live and accessible parts. And then, so what that does, normally the plug will be like a two-pin plug without any earth connection. So what will usually happen in that case is that between the user and the live parts, if there is a breakage of insulation, like we are saying there are 2 layers, it will only be one of the layers that will break down. And then for the third class, for the class 3 device, there's also how they do this is to isolate the circuit from the main supply by means of a safety isolating transformer. So generally, this is not just about medical devices. For all devices, these are the classes that we have. And what that says is that is the method of protecting people from electric shock. Let me hide this. So this is, it defines the method of protecting against electric shock. So another thing we need to think of is the medical equipment type. And this defines the degree of protection against electric shock. So in this case, we have type B, type BF, and type CF. F there means floating. And that is that the additional appliances that are floating that are not connected to the earth. Now, these 3 types is applicable to any class of equipment, any class of medical equipment. Now, if you look at the first one, it's saying that you will class a medical device as a type B, whether it is class 1, class 2, or class 3, if there is no electrical contact with the patient. Now, and whatever connection you have with the patient from that equipment is not conductive. So that's what it means. And examples are MRI, body scanners, hospital beds, phototherapy equipment. Secondly, the second type of medical devices we have is the BF. And this is safe for electrical connections between the patient, but there will be no direct connection to the heart. So we have patient parts, like the applied parts of the device is isolated. So there is no connection between the floating parts of the device to the earth. So examples of this is blood pressure monitors, incubators, ultrasound equipment. And if a device can be used in combination with a defibrillator, then you will have this sign. You can compare the normal sign to this sign. And then thirdly, we have the third type of device, which offers the highest degree of protection, and it is safe to connect to the patient's heart. And the AP is also isolated from the earth, like we had in the case of the BF. So in this case, the permitted leakage current is much lower than either of the 2 types that we've considered. An example is a dialysis machine. So I will just run through the most important tests for an electrical safety test. If you want to know about more of that, you can check that standard 6601. It is very clear about what we need to do. But the things to note is that for electrical safety of our medical devices, we need to do protective earth continuity tests, insulation resistance tests, earth leakage current tests, touch current stroke enclosure leakage current test, and patient leakage current test. Now, we have diagrams in that documentation that shows how the connections should be. And mind you, we need people who are qualified to handle these things, to do them. Now, these are some of our test equipment and tools. We all know what a multimeter is. Now, this is an electrical safety analyzer. We have this in my lab, and we've used it to carry out some field studies in some for example, in Benin. We went to Benin and we were just testing the quality of the electrical systems in the hospitals there, and we used this equipment for that. It really came in handy. And this one is it analyzes the quality of your network, and these are very expensive equipment, and a regular hospital may not have it. So, but whatever is needed to be done can be done with the digital multimeter. So, to cap all I have said so far, I'm going to just summarize with this video, just as a reminder of what I have said about medical, the safety of medical equipment. If we want to know more about that, we can go online to find more. So let me just play this.
Okay, sorry, Ma, we have a few more minutes.
Biomedical Engineers TV. If you are watching this video first time, I encourage you to begin with the first part of this video to understand the electrical safety standards of medical equipments. In this last video, we will cover up the medical equipment type. The class of equipment defines the method of protection against electric shock. The degree of protection for medical electrical equipment is defined by the type designation. The reason for the existence of type designations is that different pieces of medical electrical equipment have different areas of application, and therefore different electrical safety requirements. For example, it would not be necessary to make a particular piece of medical electrical equipment safe enough for direct cardiac connection if there is no possibility of this situation arising. Let's begin know about Type B equipment. Type B is the least stringent classification and is used for applied parts that are generally not conductive and can be immediately released for the patient. Equipment providing a particular degree of protection against electric shock, particularly regarding allowable leakage currents and reliability of the protective earth connection, if present. The next type is BF type equipments. Type BF is less stringent than CF and is generally for devices that have conductive contact with the patient or having medium or long-term contact with the patient. Type B applied parts may be connected to earth, while Type BF and CF are floating and must be separated from earth as Type B, but with isolated or floating F-type applied part or parts. And the last one is the CF type equipments. Type CF is the most stringent classification, being required for those applications where the applied part is in direct conductive contact with the heart or other applications as considered necessary. Equipment providing a higher degree of protection against electric shock than Type BF, particularly with regard to allowable leakage currents and having floating applied parts. I hope you understood the electrical safety standards of medical equipment in a simple manner. I request please go through the testing process as per the electrical safety device procedure, as every manufacturer has their own protocols. Thanks for watching, and don't forget, subscribe the channel.
Right.
See you guys.
So thank you. So I have come to the end of my presentation, but before I go, I want you to do something for me. I want some feedback on the presentation. So I'm just going to go to please go to my screen, my page again. And let me activate the activity. There's a poll there that I want you to, I'll just keep this other one. So let me activate this. The poll is on. So please just please take part in the poll. Meanwhile, I can take your questions now. Whatever questions that we have. Thank you.